Saturn radiates 2.7 times more energy into space than it receives from the Sun. This giant planet generates its own internal heat source, pumping out millions of watts from its core. The temperature at Saturn's center reaches 11,600 degrees Celsius, hotter than the surface of the Sun. That heat has to go somewhere, and it drives storms that dwarf anything on Earth. At Saturn's North Pole, a hexagonal jet stream spans 30,000 kilometers across. The winds along its edges blow at 320 kilometers per hour, faster than the most violent hurricane ever recorded. This hexagon has persisted for at least 40 years, possibly centuries. No one knows why it exists or what keeps its shape locked in place. Scientists thought Saturn was serene because its storms looked small through telescopes. They were wrong. The atmosphere conceals violence on a planetary scale. The hexagon alone could swallow 4 Earths. Inside it sits a hurricane 2,000 kilometers wide with winds reaching 530 kilometers per hour. That excess heat from Saturn's core fuels atmospheric chaos across the entire planet. The energy difference creates pressure systems that never stop, storms that never die, winds that never rest. Saturn is not the peaceful gas giant of posters and screensavers. It is a heat engine wrapped in hydrogen, spinning at 10 hours and 33 minutes per rotation, generating its own weather system that operates on rules we barely understand. If you find this terrifying, hit that like button and subscribe. As we begin now, you've seen Saturn through a telescope, maybe your own, maybe at an observatory on a school field trip, maybe in photographs shared by astronomers online. It appears as a golden jewel suspended in darkness. The rings stretch out like silk ribbons catching distant sunlight. The planet glows with a soft, warm color that suggests autumn evenings and calm summer days. Saturn looks serene. It looks peaceful. It looks like the kind of place where nothing bad could ever happen. Saturn sits 1.2 billion kilometers from Earth. That's far enough that light, moving at 300,000 kilometers per second, takes over an hour to make the trip. When you look at Saturn, you're seeing it as it was over an hour ago. You're looking backward through time across a distance your mind can't really hold. But distance does something else too. It hides the truth. In 2017, Cassini recorded something. The spacecraft had been orbiting Saturn for 13 years, sending back images of those elegant rings and that butterscotch atmosphere. Then scientists converted Saturn's radio emissions into sound waves humans could hear. They expected hums, maybe gentle static, the kind of ambient noise you'd associate with a peaceful giant floating through space. They heard screaming, Saturn screams, and we never knew because we were only looking, never listening. This is the part that keeps me up at night. We've been looking at Saturn for 400 years, thinking it was peaceful. We were wrong the entire time. Space is not silent. That's the first surprise. Most people imagine the vacuum of space as perfectly quiet. And technically that's true for sound waves. Sound needs molecules to vibrate through. Space has almost none, but radio waves travel just fine through nothing. Saturn produces intense radio emissions, electromagnetic waves that pulse and shriek across frequencies we can't hear with our ears. When those waves get converted down into audible frequencies, the result sounds genuinely terrifying. Deep howls, high-pitched shrieks, the grinding of forces you can't identify. It sounds like something dying or something hunting. The radio emissions are Saturn's true voice, and it's not singing, it's howling. Think about what that means. Every photograph you've ever seen of Saturn shows you photons, visible light bouncing off cloud tops and rings, traveling across space, hitting a camera sensor or your retina. Photons are beautiful, and they show you color and shape and the delicate structure of ice particles catching sunlight. But photons only tell you what something looks like. They don't tell you what it is. Radio waves tell the truth. They reveal magnetic fields twisting through space. They show you electrical storms crackling through atmosphere. They expose the violence of charged particles spiraling around magnetic field lines at speeds that would vaporize anything made of matter. Saturn's radio emissions come from those processes, from the planet's magnetosphere getting battered by the solar wind, from lightning bolts 1,000 times more powerful than anything on Earth, from the interaction between Saturn's magnetic field and its rings, a process that generates electrical currents millions of amps strong. We judge Saturn by photons, but photons lie. Radio waves tell the truth. Looking at Saturn through a telescope is like watching a silent film of a war zone. You see the beauty, but you can't hear the screaming. You see the golden clouds and the pristine rings, and you think everything must be fine there, calm, orderly, a system in perfect balance. Then you listen to what Saturn actually sounds like, and you realize the silence was never real. It was just distance and the limitations of human senses conspiring to hide the violence from you. The visual serenity is real. The planet does glow with that warm light. The rings do catch the sun in ways that look impossibly delicate, but that beauty exists on top of forces that would destroy you in seconds. The same magnetic fields that generate those haunting radio emissions would radiation blast any spacecraft that got too close. And the same atmospheric dynamics that create those smooth-looking cloud bands also drive wind speeds that would shred solid metal. The peaceful appearance and the violent reality occupy the same space at the same time. Saturn is both things at once, gorgeous and lethal, serene and screaming. This disconnect between appearance and reality runs deeper than just radio emissions. It defines everything about Saturn. The rings look solid and permanent. They're not. The atmosphere looks smooth and calm. It isn't. The hexagon at the North Pole looks like some kind of stable geometric pattern. It's actually a jet stream with winds faster than any hurricane, locked in a shape nobody can fully explain. Every beautiful feature conceals something violent. Every peaceful image hides a truth about forces operating on scales that make Earth's worst storms look like gentle breezes. You can't hear Saturn scream when you look through a telescope. You can't feel the magnetic fields twisting through space or sense the electrical currents flowing between rings and atmosphere. You just see the light, and the light looks so calm that your brain fills in the rest, assumes peace where there is none, imagines tranquility in a place defined by chaos. We've been doing this for centuries. Galileo saw Saturn through his primitive telescope in 1610 and thought the rings were handles, like ears on a vase. As telescopes improved, we saw more detail, better rings, cloud bands, the gap Cassini discovered in 1675. Each improvement revealed more beauty, more structure, and more reasons to think of Saturn as orderly and peaceful. Nobody could hear what it actually sounded like until we sent a spacecraft there and built instruments sensitive enough to detect radio emissions. Only then did we learn we'd been wrong about the fundamental nature of the place. That's what the rest of this video is about. What Saturn actually is beneath the beautiful surface. Not the peaceful giant of classroom posters. Not the serene jewel floating in space. The real Saturn. The one that screams. The rings are a good place to start. They look permanent. They look like they've been there forever and will stay there forever. They haven't, and they won't. Those rings are a graveyard. They're not a permanent feature. That's the first thing you need to know. And most people look at Saturn and assume the rings have always been there, circling the planet since the solar system formed. They assume those rings will always be there, as eternal as Saturn itself. Both assumptions are wrong. The rings are a corpse, the shattered remains of a moon that got too close. Here's what probably happened. A moon, maybe the size of one of Saturn's smaller satellites today, drifted inward, or maybe its orbit decayed over millions of years. Either way, it crossed a boundary, a line in space that looks like empty, nothing but marks the point where Saturn's gravity becomes more powerful than the moon's ability to hold itself together. Scientists call this the Roche limit. It's not a metaphor. It's a real distance where tidal forces overcome a moon's own gravity. Imagine Saturn's gravity grabbing the near side of that moon, pulling it toward the planet. At the same time, the far side is farther away, so the pull is weaker there. The moon gets stretched. The near side accelerates inward. The far side lags behind. The difference in gravitational pull across the moon grows stronger as it gets closer. Eventually, the moon can't hold itself together anymore. It doesn't explode. It just comes apart, piece by piece, then all at once. The moon that was becomes the rings that are. That's not ancient history. That's a crime scene. The evidence is still there, orbiting Saturn at 17,000 kilometers per hour. The rings stretch 282,000 kilometers from edge to edge. That's 175,000 miles. Picture the distance from Earth to the moon. Now picture all of that space filled with spinning, colliding chunks of ice. The rings are that wide. They span a distance that would take light almost a full second to cross. If you stood at one edge and looked toward the other, you couldn't see the far side. It would be beyond the curve of your vision, lost in the vastness. But here's the thing that makes them strange. Despite all that width, the rings average only 10 meters thick in many places. That's 30 feet. 3 school buses stacked on top of each other. If you built a scale model the width of a football field, the thickness would be thinner than a sheet of paper. You could almost call them two-dimensional, a disk so thin that if you approached from the right angle, they would disappear. Edge on. There's almost nothing to see. What's in those rings? Water ice. 99.9% pure, the purest ice in the solar system, orbiting a planet that could swallow 1,000 Earths. Each particle is a shard of that destroyed moon, flash frozen and preserved. Some pieces are microscopic, dust grains smaller than the width of a human hair, drifting in formation with billions of others. Some pieces are the size of pebbles, some are car-sized, some are as big as houses. All of them ice, all of them spinning in the same direction, held in orbit by the gravity of the planet that killed their parent moon. Think about the scale for a second. Billions of chunks of ice, ranging from dust to buildings, all orbiting in a layer thinner than a 10-story building is tall. They collide constantly. The smaller pieces grind against each other, creating more dust. And the larger pieces break apart when they hit, creating more fragments. The rings are not stable. They're not peaceful. They're a slow-motion grinding process that's been going on for however long the rings have existed. Nobody knows exactly when that moon died. The rings might be 100 million years old. They might be younger. Recent evidence suggests they could be as young as 10 million years, which in cosmic terms is yesterday. Dinosaurs walked the Earth longer than these rings have existed. That's the part most people don't realize. The rings aren't primordial. They're not a feature Saturn was born with. They're something that happened recently. The rings are also evidence of how dangerous proximity can be. That moon didn't crash into Saturn. It didn't hit anything. It just got too close. The Roche limit for an icy moon around Saturn sits at about 2.4 times Saturn's radius. Cross that line and tidal forces win. Your structure loses. The moon becomes debris. The debris becomes rings. This is what Saturn does. It pulls things in. It tears them apart. It grinds them down into particles so fine they look smooth from a distance. The rings aren't decoration. They're a warning. They're what happens when something crosses the line and can't go back. A graveyard, yes, but also a demonstration of gravitational violence playing out in slow motion. Beautiful from far away, lethal up close. The rings won't last forever either. They're already falling. Particle by particle, they're spiraling inward toward the planet below. Rain made of ice, pulled down by the same gravity that created the rings in the first place. Saturn is eating its own crime scene, erasing the evidence of what it did. But that's a story for what comes next. Saturn is eating its rings, right now, as you're listening to this. The process has a name, ring rain. It sounds poetic. It isn't. It's gravitational execution in slow motion. 10,000 kilograms per second. That's the weight of 2 elephants vanishing every single second. By the time you finish this sentence, a small house worth of ice has fallen into Saturn and ceased to exist. Gone. Not relocated, not transformed, just gone. The mechanism is stranger than you'd think. These aren't particles simply falling like snow. The ice fragments in the rings become electrically charged. Static electricity, essentially. The same force that makes your hair stand up after rubbing a balloon. But at Saturn, the consequences are different. Saturn's magnetic field threads through the rings like invisible strings. When ice particles pick up an electric charge, they suddenly feel those strings. The magnetic field lines loop down from the rings into Saturn's upper atmosphere. The charged particles follow. They spiral along those field lines, pulled inexorably downward. The journey ends fast. The ice hits Saturn's atmosphere at thousands of kilometers per hour. Friction heats it instantly. The particles don't crash. They don't splash. They vaporize. One moment, solid ice. The next, dispersed atoms mixing into Saturn's clouds. The rings don't fall into Saturn. They evaporate into it. This has been happening since the rings formed. It will continue until there's nothing left to fall. We know the rate. We've measured it. Scientists watched as ring particles streamed down magnetic field lines, glowing as they burned up. They calculated the mass loss. 10,000 kilograms per second isn't an estimate. It's an observation. Do the math, and something troubling emerges. At this rate, the rings can't be old. They can't have existed for billions of years, since Saturn formed. There isn't enough mass. If the rings were ancient, they'd be gone already. The math doesn't work unless the rings are young, very young. The rings are only 10 to 100 million years old. Let that number sit for a moment. The earliest dinosaurs appeared on Earth around 230 million years ago. When Eoraptor was hunting in what would become Argentina, Saturn had no rings. When the first dinosaurs looked up at the night sky, Saturn was a dim yellow dot, unbeautiful, maybe, but unremarkable. Just another planet. The rings didn't exist yet. The rings are younger than the dinosaurs. T-Rex lived and died on a planet where Saturn was ringless. The most famous feature in the solar system is newer than fossils, newer than the Atlantic Ocean, newer than the Rocky Mountains. In cosmic terms, the rings appeared yesterday. This changes everything about how we see Saturn. Most images make the rings look eternal, permanent, a feature as old as the solar system itself. That's the assumption. It feels right. Something that beautiful, that vast, should be ancient, should be stable, should be forever. It isn't. The rings are temporary, an accident of timing. Something wandered too close. Something crossed the Roche limit. Something died. And for a brief window, cosmically speaking, a Saturn wore a crown. We happened to show up during that window. We happened to evolve eyes and build telescopes during the exact era when the rings exist and look spectacular. Think about the timing. Saturn is 4.5 billion years old. The rings have existed for maybe 100 million years at most. That's 2% of Saturn's lifetime. 2% for 98% of its existence. Saturn was ringless. For 98% of its future, it will be ringless again. We are living in a cosmic blink of an eye. A few million years earlier, no rings. A few million years later, no rings. We showed up at exactly the right century out of billions. That's not luck. That's winning a lottery we didn't know we'd entered. The rings won't last. Another 100 million years, maybe less, and they'll be gone. Completely. Ring rain will consume them entirely. Saturn will return to what it was before, a gas giant with moons and storms and nothing else. The crown will disappear. Future astronomers, if any exist, will look at Saturn and see a planet much like Jupiter, banded, rotating, alone. They might find evidence. Maybe faint traces in Saturn's atmosphere, anomalies in the magnetic field, clues that something once orbited where now there's only empty space. They'll reconstruct what happened. They'll build models. They'll calculate that yes, once Saturn had rings, and those rings were glorious, but they won't see them. They'll miss it by millions of years, and they'll know what they missed. They'll look at our photographs and our data and feel something like envy, or loss, or both. We won't miss it. We're here, right now, and in the window. We get to see Saturn with rings. We get to watch them catch sunlight and cast shadows and shimmer in Cassini photographs. We get to know what they look like up close, what they're made of, how they sound when a spacecraft passes through. We get all of it. Not because we're special, because we're lucky. Cosmically, absurdly, impossibly lucky. But luck runs out. For Saturn, the countdown started the moment the rings formed. Every second, another 2 elephants worth of ice. Every hour, another 72,000 tons. Every year, the rings get slightly thinner, slightly less massive, slightly closer to gone. The process is irreversible. There's no mechanism to replenish what's lost, no source to replace the ring rain. Saturn is spending its capital, and capital doesn't regenerate. The graveyard we talked about earlier isn't just a graveyard, it's an evaporating graveyard. Evidence disappearing even as we study it. A crime scene being erased while investigators are still working. Saturn isn't just dangerous to moons, it's dangerous to its own history. It destroys, then it covers up. It kills, then it consumes. The rings are both the evidence and the victim. Everything beautiful about Saturn is temporary. The colors will fade as the rings thin. The shadows will soften. The gaps will close. Cassini's division, the Encke gap, the ringlets and braids and shepherd moons, all of it will collapse inward. The structure will dissolve. Complexity will give way to simplicity, then to nothing. And Saturn itself won't change, won't mourn, won't notice. The planet below the rings is indifferent. It takes what falls. It spins, it radiates, it continues. Whatever violence created the rings, whatever chaos reigns inside Saturn's interior, none of it cares about beauty. None of it cares about timing. The universe doesn't pause for elegance, but we do. We notice. We care. We point telescopes and send spacecraft and write scripts about rings that won't last. Maybe that's what makes them matter. Not that they're eternal, that they're not. Here's what gets me about Saturn. The planet that rips moons apart and swallows its own history isn't what you'd call heavy. The word doesn't fit. Saturn is massive, yes, 95 times the mass of Earth, but dense? No. Saturn is the least dense planet in the solar system, by a lot. 0.687 grams per cubic centimeter. That's Saturn's density. Water, the stuff you drink, the stuff in your tap, sits at 1.0 grams per cubic centimeter. Saturn is lighter than water, less dense than the liquid you shower in every morning. Think about that for a second. This planet, this thing that tears rings into existence and crushes everything that falls toward it, would float if you had a bathtub large enough, and I mean truly absurd, larger than the Sun. Saturn would float in it. The only planet in the solar system that could do that. It's less dense than water. Jupiter wouldn't float, neither would Uranus or Neptune. Earth certainly wouldn't. Just Saturn, the ring destroyer, the moon grinder, the planet with gravity strong enough to bend light and warp space. That's Saturn. It floats. This is the paradox. Saturn doesn't feel light when you look at the numbers. It's 95 times the mass of Earth, 95 Earths worth of matter pulled into one spinning ball. That's not small. That's not insignificant. But then you look at the volume. You could fit 760 Earths inside Saturn's volume. 760, but it only weighs as much as 95 Earths. It's huge, but mostly nothing. Hydrogen gas compressed into a ball. The math works out to something absurd. Saturn is so large and so light that its average density drops below water. Not because it's hollow, not because there's empty space inside, because it's made almost entirely of the lightest elements in the universe, hydrogen and helium, the same stuff that fills birthday balloons and makes stars burn. Compressed, yes. Under enormous pressure, yes. But still fundamentally light, still less dense than the water in your glass. This contradicts every intuition you have about planets. Big things should be heavy. Dangerous things should be solid. A planet that destroys moons should be dense, compact, made of iron and rock and things that have weight. Saturn defies this. Saturn is a ghost, a massive planet-eating ghost made of almost nothing. Here's where it gets strange. Despite being light, despite floating on water, Saturn still has crushing gravity. Mass is mass. 95 Earths is 95 Earths, no matter how spread out. The gravity at Saturn's cloud tops is only slightly stronger than Earth's, about 1.06 times what you feel right now. You could almost stand there if there were anything to stand on. But there isn't. There's no surface, no ground, no place where atmosphere ends and planet begins. If you tried to land on Saturn, you wouldn't. You'd just sink. The atmosphere would thicken around you. The hydrogen gas would get denser with every kilometer you fell. The pressure would climb. The temperature would rise. You'd sink through clouds, then through fog, then through something that isn't quite fog anymore. The air would press in from all sides. Your ship, your suit, your body, all of it would start to buckle. A falling into Saturn would be like sinking through fog that gets thicker with every meter until the fog becomes liquid. Then the liquid becomes something that isn't liquid or gas, and then you're crushed into a smear of atoms. There's no ground, there's no landing, just deeper and deeper wrongness until you stop existing. The transition is gradual. The death is not. The pressure climbs to levels that don't exist on Earth. Millions of times atmospheric pressure. At those extremes, hydrogen stops behaving like a gas. It doesn't turn into liquid the way water does when you cool it. It just gets compressed, squeezed. The atoms pack closer and closer until the substance becomes something called a supercritical fluid. Not gas, not liquid. Both, neither. Something in between that only exists under conditions so extreme we can barely study it. You'd be crushed long before you reach that layer. Your body would fail at a fraction of the pressure. Metal would crumple. Diamond would crack. Nothing we can build survives that deep. Nothing biological stands a chance. Saturn's low density doesn't save you. The mass does what mass always does. It pulls. It compresses. It wins. This is the trick Saturn plays. It looks light. It is light, by planetary standards. But light doesn't mean safe. Light doesn't mean gentle. Saturn is 760 Earths worth of volume filled with 95 Earths worth of mass. And all of that mass wants to collapse into the center, wants to crush itself into something smaller, denser, more compact. Yet the only thing stopping it is the pressure of hydrogen pushing back, the heat from Saturn's core pushing outward, the spin spreading everything into an oblate spheroid. But the urge to collapse never stops. The gravity never rests. Saturn is constantly falling into itself and constantly pushing back, a planet-sized battle between compression and expansion. You'd be caught in the middle of that battle, sinking through layers of hydrogen that get hotter and denser and stranger the farther you fall. There's no bottom, no core you could land on. At least, not one we've ever seen or measured. Just pressure climbing toward infinity and temperature climbing with it. The planet that floats is also the planet that crushes. The lightest planet in the solar system is still heavy enough to tear moons into rings and grind those rings into dust. A mass and density aren't the same thing. Saturn proves it. You can be light and still be lethal. You can float on water and still destroy everything that comes near you. And deep inside, where the pressure becomes unimaginable and the temperature rivals the surface of the sun, Saturn stops being the peaceful gas giant we imagine. It becomes something else, something hot, something violent, something that would make the rings above look calm by comparison. Inside Saturn, the rules change. The pressure climbs, the temperature climbs, and somewhere in that crushing darkness, carbon atoms in the atmosphere get squeezed so hard they become something else. Something solid. They become diamonds. This isn't speculation. The math requires it. Saturn's atmosphere contains methane, which is carbon and hydrogen. As you descend, as the pressure grows so intense that the methane breaks apart, the hydrogen separates, the carbon remains, and under that much pressure, carbon doesn't stay as gas. It can't. The atoms compress into soot first, black particles drifting in the hydrogen haze. Then the pressure increases. The soot compresses further. It becomes graphite, the same material in pencils. Still carbon, but arranged differently, denser, harder. But Saturn doesn't stop there. Go deeper, where the pressure reaches millions of times what we experience at sea level, and the graphite compresses even more. The atomic structure shifts again. The carbon atoms lock into a crystal lattice. They become diamonds, actual diamonds, forming in the clouds, falling through layers of hydrogen like rain. Picture rain on Earth, water droplets falling from clouds, hitting leaves, splashing in puddles. That's what happens inside Saturn, except the rain is diamonds. Some as small as dust, some potentially the size of hailstones, falling through the atmosphere, sinking deeper into the planet. Most people have never heard of diamond rain. It sounds like something from a fantasy novel, but it's real physics. The pressure and temperature conditions inside Saturn mathematically require this to happen. We've recreated similar conditions in laboratories on Earth. We've watched carbon transform under extreme pressure. The same process happens inside Saturn, just on a planetary scale. The diamonds fall. They sink through layers of hydrogen that keep getting denser. The temperature climbs as they descend, 11,700 degrees Celsius at the core, and that's 21,000 degrees Fahrenheit, hot enough to melt titanium, hot enough to vaporize rock, and hot enough to do something strange to diamonds. They melt. Actually, that's not quite right. Let me try again. The diamonds don't just melt, they cease being diamonds. The pressure is so high that the atomic structure can't hold. They become something else. We don't have a good word for it because it doesn't exist anywhere we can touch. Liquid carbon, oceans of it, pools of melted diamond flowing through Saturn's interior. Think about that. There are oceans inside Saturn. Not water, not liquid hydrogen, liquid diamond, floating on denser layers below. We can't see them, we can't reach them, but they're there, deep in the planet's interior. A sea of melted carbon that was once falling as rain. In it, the atmosphere above transitions into something equally strange. As you descend, the hydrogen doesn't just get thicker, it enters a state that shouldn't exist, a supercritical fluid. This is what happens when you squeeze something so hard that the difference between gas and liquid stops meaning anything. It's both, it's neither. It's a state of matter that doesn't exist on Earth outside of laboratories. On Earth, water is ice, or liquid, or steam. 3 states, distinct boundaries. You can see when water boils. You can see when it freezes. There's a clear line. But if you increase the pressure and temperature enough, that line vanishes. The water becomes supercritical. It has the density of a liquid, but flows like a gas. It fills containers like a gas, but dissolves materials like a liquid. The rules break down. And that's what Saturn's interior is. Supercritical hydrogen, a gradient where gas becomes thick, thick becomes fluid, fluid becomes hot, hot becomes a plasma soup of hydrogen and helium and melted diamonds. There's no surface to land on, no boundary to cross, just a continuous transition from the thin atmosphere above to the hellish core below. The core itself isn't solid. There's probably rock and metal down there, remnants from Saturn's formation. But it's not a core you could stand on. It's more like a gradient, everything compressed and heated until it's all mixed together. A molten center surrounded by liquid diamond, surrounded by supercritical hydrogen, surrounded by falling diamond rain, surrounded by clouds of methane and ammonia. And it's hot, not just warm, not just uncomfortable. Hot enough that the core rivals the surface of the sun, 11,700 degrees Celsius. That's twice as hot as molten lava, 3 times hotter than the hottest furnace we've ever built. All of that heat trapped inside a planet that looks cold and peaceful from the outside. The heat pushes outward. The pressure pushes inward. Diamonds form and fall and melt. Hydrogen transitions between states that don't have names. Carbon floats in liquid oceans we'll never see. And all of it happens in darkness. No light reaches Saturn's interior. No sunlight penetrates that far. Just crushing pressure and searing heat and matter behaving in ways that seem impossible. This is the forge at the center of the floating planet, the violence hidden beneath the serene exterior. Saturn doesn't just have rings and moons and a gentle golden glow. It has a heart of fire, a core hot enough to destroy anything that gets close. Oceans of liquid diamond, rain made of crystals, and layers of hydrogen compressed into states that physics barely allows. The planet that looks peaceful is manufacturing diamonds in its atmosphere and melting them in its core. The planet that floats on water contains temperatures that would vaporize water instantly. The lightest planet in the solar system has an interior dense enough to crush carbon into crystal and hot enough to turn crystal into liquid. And we haven't even reached the surface yet, because Saturn's surface is where the real violence happens, where the heat from below meets the cold from above, where the spin and the pressure and the chemistry collide, or where storms form that make Earth's hurricanes look like gentle breezes. The interior is a forge, but the exterior is a battlefield. The exterior is a battlefield, and at the North Pole, there's something waiting, something that shouldn't exist. A hexagon, not a circular storm, not an oval, a hexagon. 6 straight sides, 6 sharp corners, a geometric shape carved into the clouds of Saturn like someone took a ruler to a hurricane. The hexagon is a geometric ghost. It doesn't drift, it doesn't wobble. It just exists, locked to the pole, a 6-sided jet stream that defies the chaos of everything around it. Each side of the hexagon stretches roughly 13,800 kilometers. That's 8,600 miles. To put that in perspective, you could fit the entire United States along one side and still have room left over. One side. There are 6 of them. The entire structure spans more than 29,000 kilometers across. 2 Earths could fit across the hexagon, not 2 Earths stacked. 2 Earths side by side, and the hexagon would still have room. It's a storm system the size of a planetary collision, but it's been sitting there, unmoving, for decades. We first saw it in 1980, when Voyager 1 flew past. A strange 6-sided pattern at the pole. Scientists thought maybe it was a glitch, a processing error, something wrong with the image. Then Voyager 2 confirmed it a year later. Same hexagon, same position, same shape. Then Cassini arrived in 2004, more than 20 years after the Voyager flybys. The hexagon was still there, exactly where it had been, the same 6 sides, the same dimensions, a geometric storm that hadn't moved or changed shape in over 2 decades. Storms on Earth last days, sometimes weeks if they're massive. Hurricane Katrina lasted 7 days. The Great Red Spot on Jupiter has lasted centuries. But it drifts, it shrinks, it changes. Saturn has a geometric storm that has persisted longer than human spaceflight. We've been watching it for over 40 years now. It hasn't budged. The winds along the hexagon's edges scream at 320 kilometers per hour. That's 200 miles per hour, faster than the strongest tornado ever recorded on Earth, and those winds just keep going, tracing 6 perfect straight lines, turning sharp 90-degree corners, then continuing on to the next side. Think about that. A wind doesn't move in straight lines. Wind curves, wind spirals. Wind follows pressure gradients and temperature differences and the rotation of the planet. Wind is chaos made visible. But on Saturn, at the North Pole, wind has been drawing a hexagon for longer than most people have been alive. At the center of the hexagon is a hurricane. The eye alone is 2,000 kilometers wide. That's 50 times wider than the worst hurricane Earth has ever produced. And that eye is just the center of a structure that dwarfs continents. The hurricane rotates. The hexagon doesn't. The storm at the center spins like any other cyclone, but the 6-sided jet stream around it stays locked in place. A rotating core inside a stationary geometric frame. It's like watching the hand of a clock spin while the clock face refuses to move. Yet we know what causes the hexagon. Sort of. It's a standing wave pattern in fluid dynamics. Different layers of Saturn's atmosphere rotate at different speeds. Where fast winds meet slower winds, waves form. Under very specific conditions, those waves can lock into stable geometric patterns. You can recreate this effect in a laboratory. Put fluid in a rotating cylinder. Spin a smaller cylinder inside it at a different speed. Under the right conditions, the fluid between them forms polygons, triangles, squares, hexagons, pentagons. The number of sides depends on the speed difference and the properties of the fluid. Saturn's hexagon is that same phenomenon, scaled up to planetary size. The jet stream at the pole rotates faster than the atmosphere around it. The speed difference creates waves. 6 waves. They lock together. They stabilize. They persist. But here's the part we don't fully understand. Why 6 sides? Why not 5? Why not 7? The fluid dynamics can explain why geometric patterns form. They can't explain why this specific pattern is so stable, or why it stays exactly 6-sided, or why it hasn't drifted or dissipated in over 40 years. We still don't have complete answers. The math works in general terms. The specific case of Saturn's hexagon still has gaps. Scientists can simulate hexagons in the lab, but the simulations don't perfectly match what we see at Saturn. Something about the stability is different, something we're missing. The hexagon changes color with the seasons. Saturn's year lasts 29.5 Earth years, so each season is roughly 7 years long. When Cassini first arrived, so the North Pole was in winter darkness. The hexagon was a deep blue. As spring came to the northern hemisphere, the hexagon shifted to gold. Same shape, same position, different color. The seasons change. The geometry doesn't. Cassini watched the hexagon for 13 years. Thousands of images, different wavelengths, different angles, different lighting conditions. Every image showed the same thing. 6 sides, sharp corners, unmoving. The most monitored storm in the solar system. And it never did anything unexpected. It just existed, permanent, geometric, locked to the pole like it was carved there. There's something deeply unsettling about a storm that doesn't move. Storms are supposed to be temporary. They form, they rage, they dissipate. They're chaos incarnate. But the hexagon is orderly chaos. Yet its violence arranged into geometry. It's a hurricane that obeys rules we barely understand. The hexagon is not unique because it's large. Saturn has plenty of large storms. It's not unique because it's violent. Saturn's entire atmosphere is violent. It's unique because it stays, because it maintains a perfect 6-sided shape for decades without drifting or dissipating, because it's a reminder that Saturn doesn't follow the same rules as Earth, or Jupiter, or any other planet we've studied. And the hexagon, massive as it is not Saturn's only storm. It's not even the most violent one. It's just the most persistent, the most geometric, the strangest, because Saturn has other storms. Storms that make the hexagon look calm by comparison. Storms that appear, rage with impossible fury, then vanish for decades. Storms that we still can't predict or fully explain. The hexagon is a warning, a geometric ghost at the pole, showing us that Saturn's atmosphere operates on a scale and with a stability that defies everything we know about weather. And it's just the beginning of what happens when you have a planet this big, spinning this fast, generating this much heat from within. The hexagon is permanent. It's been there for decades, probably centuries. But Saturn has another storm, one that doesn't stay, one that appears, erupts with violence that makes the hexagon look tame, then vanishes for 30 years. We call it the Great White Spot. It's not a spot. Not really. It starts as one, a bright eruption in Saturn's atmosphere, but it doesn't stay small. It grows. Within weeks, it stretches. Within months, as it wraps around the entire planet like a belt, encircling Saturn's equator. Imagine a storm on Earth that started in New York and grew until it touched itself on the other side of the globe. That's the scale we're talking about. A storm that consumes an entire planetary circumference. 400,000 kilometers of continuous tempest. The Great White Spot doesn't happen randomly. It follows a schedule. Every 30 Earth years, almost exactly, Saturn's atmosphere tears itself apart in the same way. 30 years. 1 Saturnian year. 1 complete orbit around the Sun. Then, the planet convulses again. We saw one in 1933. Amateur astronomers spotted a bright white patch near Saturn's equator. It grew over months, wrapped around the planet, then faded. Another appeared in 1960, then 1990, then 2010, when the Cassini spacecraft was there to watch it happen. The pattern holds. 30 years. Like clockwork. We don't really know why the cycle is so precise. Why 30 years? Why not 25 or 35? The best guess is that it's tied to Saturn's orbit. 1 year on Saturn, 1 great white spot. But that's correlation, not causation. The honest answer is we don't know. Saturn keeps its secrets. What we do know is what these storms contain. Lightning. Not the kind you see during Earth thunderstorms. Something far more violent. 1 lightning bolt from the Great White Spot contains the energy of 10,000 Earth lightning strikes hitting at once. 10,000. The Cassini spacecraft detected them through radio emissions, massive bursts of electromagnetic energy that screamed across space. Each bolt releases more power than entire terrestrial storms produce in hours. If you could somehow survive in Saturn's atmosphere during this event, the lightning wouldn't just kill you. It would vaporize you and everything within kilometers. The shockwave alone would tear apart anything solid. Earth's most powerful lightning strikes release about 1 billion joules of energy. That's enough to power a typical home for a month. Saturn's superbolts release 10 trillion joules. That's enough energy to power a small city for a year, per bolt. And during the Great White Spot, these superbolts fire constantly, hundreds per hour, thousands per day. The storm doesn't just produce lightning, it becomes lightning, a continuous planetary-scale electrical discharge that wraps around an entire world. The Cassini spacecraft recorded the radio signatures from 3.5 million kilometers away. That's 9 times the distance from Earth to the Moon. The storm was so powerful, so electrically active, that its signal overwhelmed Cassini's instruments. Engineers had to recalibrate the sensitivity just to measure it without causing damage. These aren't weather patterns. Not in any sense we understand weather. Every 30 years, Saturn has a planetary convulsion. Heat that's been building in the interior, trapped beneath layers of hydrogen and helium, suddenly breaks through. Yet the atmosphere doesn't just storm, it erupts. It's more like a planetary-scale seizure than a weather system. The entire band of atmosphere where the Great White Spot forms becomes unstable. Temperatures spike, winds accelerate, and the lightning begins. The 2010 storm lasted for months. It started as a small bright patch, barely visible from Earth. Within weeks, it had grown to 8,000 kilometers across. Within 2 months, it had stretched into a band that wrapped entirely around Saturn's equator. The head of the storm eventually caught up with its own tail, creating a continuous loop of destruction. One storm, 400,000 kilometers of circumference. No beginning, no end. Just perpetual violence feeding back into itself. Then it faded, not quickly. Over months, the Great White Spot dimmed, broke apart, it dissipated into Saturn's background atmosphere. By 2011, it was gone. The atmosphere settled back into its normal chaos. The superbolts stopped. Saturn looked peaceful again, from a distance. But the heat is building again. Deep in Saturn's interior, energy is accumulating. Convection currents are stirring. Somewhere in the 2030s or 2040s, depending on the exact timing, it will happen again. The atmosphere will tear open. The Great White Spot will return. And for months, Saturn will wrap itself in a storm that contains more energy than all of Earth's weather systems combined. We can predict when. We just can't explain why. Why does the cycle match Saturn's year so precisely? What triggers the eruption? Why does it always happen at roughly the same latitude? These are questions without answers. But we can watch, we can measure, we can document the violence, but we can't explain the mechanism that makes a planet convulse on schedule. Most people think of Saturn as the peaceful planet, the pretty one with rings. They don't know about the hexagon. They don't know about the superbolts. They certainly don't know that Saturn erupts like clockwork, wrapping itself in electrical fury every 3 decades. The surprise isn't just that these storms exist, it's that they're predictable. Saturn's violence follows rules, 30-year rules that we observe but don't understand. The Great White Spot is a reminder that Saturn's atmosphere is never calm. The hexagon shows us persistent geometric violence. The Great White Spot shows us periodic explosive violence. Together, they paint a picture of a world where the atmosphere itself is a weapon, and where peace is an illusion created by distance, where the pretty planet with the elegant rings is actually a gas giant that regularly tears itself apart from the inside out. And the violence doesn't stop at Saturn's atmosphere. It extends outward, to the rings, to the moons, to the satellites that orbit through Saturn's magnetic field and radiation belts. Because Saturn isn't just a planet, it's a system, a family of worlds held together by gravity. And every member of that family lives under Saturn's influence, under Saturn's violence. The violence doesn't stop at Saturn itself. It extends outward, to the moons that orbit through Saturn's radiation, through its magnetic field, through the debris rings that circle the planet like a circular saw. Over 60 moons orbit Saturn. Some are tiny, irregular rocks. Others are worlds in their own right. And one of them is stranger than almost anywhere else in the solar system. Titan, Saturn's largest moon, the second largest moon in the entire solar system. It's bigger than the planet Mercury. But size isn't what makes Titan strange. What makes Titan strange is that it has weather, it has clouds, it has rain, It has rivers that flow into lakes that drain into seas. It has a thick atmosphere. It has surface pressure you could survive without a spacesuit. It has a complete hydrological cycle, just like Earth, except nothing on Titan is water. Titan is the only moon in the solar system with a thick atmosphere. Not a thin wisp of gas, a real atmosphere. Thicker than Earth's, the surface pressure on Titan is 50% higher than what you're experiencing right now. Yet you could walk on Titan without a pressure suit. You wouldn't need protection from vacuum, just from the cold and from the chemistry. The atmosphere is 95% nitrogen. Just like Earth's, the other 5% is methane. That methane is the key to everything, because at Titan's temperature, methane does something strange. It behaves like water does on Earth. The surface temperature on Titan is minus 179 degrees Celsius. That's minus 290 degrees Fahrenheit. Cold enough that water ice is harder than granite. Cold enough that methane becomes a liquid. Cold enough that an entire water cycle gets replaced by something else. A methane cycle. Titan has methane clouds, methane rain, methane rivers flowing across the surface, carving channels through terrain made of frozen water ice and organic compounds. Those rivers drain into methane lakes. Some of those lakes are small, others are seas. Kraken Mare, the largest sea on Titan, is bigger than Earth's Caspian Sea, bigger than the largest lake on our planet. But Kraken Mare isn't water. It's liquid methane and ethane, natural gas, the stuff you burn in your stove. On Titan, it pools in basins hundreds of meters deep. Think about that. There's a world in our solar system where it rains gasoline, where lakes are filled with liquid natural gas, where clouds are made of methane vapor, and when those clouds get heavy enough, it rains. Methane rain falls from methane clouds, lands on terrain made of frozen smog, and flows downhill into seas of liquid hydrocarbons. It's Earth's water cycle, but with gasoline instead of water. Titan is a deep freeze version of early Earth. The parallels are everywhere. Clouds, rain, rivers, lakes, seas, coastlines, deltas where rivers empty into larger bodies of liquid, erosion patterns, weather systems, seasonal changes, everything that makes Earth dynamic and alive, everything that makes our planet different from dead rocks like the moon. Titan has all of it, the same processes, the same patterns, the same cycle of evaporation and precipitation and runoff, just with completely alien chemistry. The sand on Titan's beaches isn't silicon dioxide, it's frozen smog, organic compounds precipitated out of the atmosphere, hardened by the cold into grains as hard as rock. You could pick up a handful of that sand. It would feel like sand. It would pour through your fingers like sand. But it's made of molecules that, on Earth, would be toxic pollution. On Titan, they're geology. The irony is remarkable. Titan is the most Earth-like world in the solar system. It has surface features that look like home. Lakes, rivers, coastlines, archipelagos. If you looked at radar images of Titan without context, you might think you were looking at Earth. The shapes are familiar. The patterns make sense. Your brain recognizes them. This is a lake. This is a river delta. This is an island chain. But if you tried to sail a boat on Kraken Mare, the boat would corrode instantly. Liquid methane is a solvent. It dissolves most materials we use to build things. Plastics, rubbers, many metals. The sea would eat your boat before you left the shore. And if you somehow managed to float, you'd be sailing on an ocean of fuel. One spark would ignite the entire sea. Except there's no oxygen, no way for fire to burn. The ocean is flammable, but it can't catch fire. The universe doesn't care what we find convenient. Most people don't know that any moon has liquid on its surface. They picture moons as dead, airless rocks, cratered, frozen, silent. They don't picture oceans. They certainly don't picture rain. The surprise isn't just that Titan has lakes and seas. It's that these features exist at all. That there's a moon with weather, with seasons, with a landscape that changes over time because liquid moves across the surface, carving and depositing and reshaping terrain. Earth is the only planet in the solar system with stable liquid water on its surface. That's what makes Earth special. That's what makes life possible. But Titan has stable liquid on its surface too, just not water. Titan proves that you can have all the surface features of Earth, all the dynamic processes, all the complexity without water. You can have an entire hydrological cycle running on a completely different substance. You can have a world that looks like home but isn't. Titan orbits Saturn once every 16 days. It's far enough out that the radiation belts aren't as intense as they are closer in. Far enough that it's not being torn apart by tidal forces. But it's still part of Saturn's system, still subject to Saturn's gravity, still orbiting a planet that could swallow Earth 95 times over. The violence of Saturn's atmosphere doesn't reach Titan, but Titan exists because of Saturn. Its thick atmosphere, its stable climate, its methane cycle. All of it depends on Titan's position in the system, and Titan isn't the strangest moon orbiting Saturn. It's not even close. Because while Titan shows us a frozen mirror of Earth, another moon shows us something else entirely, something that shouldn't exist, something that hints at an ocean hidden beneath ice, an ocean that might be erupting into space right now. That moon is Enceladus, and it's tiny, 500 kilometers across, about the size of Arizona. You could fit it inside Texas with room to spare. Drive across it at highway speed, and you'd reach the other side before lunch. It's one of the smallest round moons in the solar system, a speck compared to Titan. Most moons that small are dead, cold rocks locked in place, no atmosphere, no activity, nothing happening except the slow accumulation of craters over billions of years. They froze solid early in the solar system's history and never woke up. Enceladus is not dead. Its surface reflects 99% of sunlight. It's the brightest object in the solar system. A perfect mirror made of ice. If you stood on it during Saturn's day, you'd be nearly blinded by reflected light bouncing off the ground beneath your feet. That much reflectivity means the surface is constantly being renewed, fresh ice replacing old. Something is resurfacing this moon. At the South Pole, there are features called tiger stripes, 4 long fissures cutting across the ice. They're warmer than the surrounding terrain, not warm by Earth standards, but warm enough that scientists noticed the temperature difference from over 1 billion kilometers away. Warm enough to matter. The tiger stripes are erupting. Water ice shoots out of these fissures at 1,300 kilometers per hour, faster than the speed of sound, faster than a bullet. These aren't gentle geysers. They're violent jets of material blasting into space. The plumes reach hundreds of kilometers above the surface before falling back down or escaping entirely. Some of that ice ends up in Saturn's E-ring, a thin ring of particles fed directly by Enceladus. The moon is creating its own ring around Saturn. Cassini flew through those plumes. We sent a spacecraft through the spray of an alien ocean and tasted it. The instruments detected water ice, salt, silica, organic molecules, everything you'd expect from an ocean in contact with a rocky core, everything you'd need for life as we know it. This raises an obvious question. Where is the water coming from? Enceladus shouldn't have liquid water. It's too small to hold on to internal heat from its formation. It's too far from the sun for solar heating to matter. It should be frozen solid all the way through, a ball of ice with maybe a rocky core in the center. That's what every model predicted before Cassini arrived. The answer is tidal heating, the same force that tears at Io around Jupiter, the same force that cracks Europa's ice, but gentler here, more sustained. Enceladus orbits Saturn in an elliptical path. Sometimes it's closer to Saturn, sometimes it's farther away, and that changing distance means Saturn's gravitational pull changes strength throughout the orbit. When Enceladus is closer, Saturn pulls harder. When it's farther, the pull weakens. That difference creates stress. The moon gets squeezed, then released, then squeezed again, over and over. Every orbit, every 33 hours. Saturn's gravity kneads Enceladus like dough, stretching it, compressing it, never letting it settle into a stable shape. That kneading generates heat through friction, the same way bending a paperclip back and forth makes it hot, the same way rubbing your hands together warms them up, except this is happening to an entire moon. Deep in the interior, ice melts. Water stays liquid despite the cold of space. The heat isn't evenly distributed. It concentrates at the South Pole, We're not entirely sure why. Something about the geometry of the orbit. Something about the internal structure. The tiger stripes sit directly over the hottest region. The ice there is thin enough that pressure from below breaks through. Water erupts into space. Beneath the ice crust, there's an ocean, a global ocean. Liquid water surrounding the entire rocky core. We know it's global because Cassini measured how Enceladus wobbles as it orbits. That wobble pattern only makes sense if there's a liquid layer between the ice shell and the core. If the ocean were just a pocket at the South Pole, the wobble would look different. Think about that for a second. A moon smaller than Texas has an ocean bigger than all of Earth's oceans combined by volume, not on the surface, hidden beneath kilometers of ice, heated by gravitational friction, erupting into space through cracks at the pole. The ocean has been there for a long time. Millions of years at least, possibly billions. Long enough for chemistry to happen. Long enough for organic molecules to form. Long enough, maybe, for something else. Nobody expected this. Before Cassini, Enceladus was barely worth a footnote. A small, icy moon. One of dozens. Scientists knew it was bright. They knew it was geologically young based on the lack of craters. But an active ocean? Plumes reaching into space? That wasn't on anyone's list of predictions. The surprise isn't just that Enceladus has an ocean. It's that we can sample that ocean without landing, without drilling through kilometers of ice. The moon is doing the work for us. It's spraying its ocean into space where we can fly through it and analyze it. No other world in the solar system offers that opportunity. Not Europa, not Mars, not anywhere. Enceladus is possibly the most likely place in the solar system to find extraterrestrial life. Not Mars with its ancient dry riverbeds. Not Europa locked beneath kilometers of solid ice. A tiny moon of Saturn that most people have never heard of. A moon so small you could drive across it in a morning. And it might be the one place in our cosmic neighborhood where life exists right now. Saturn's gravity is keeping it alive. The same gravity that creates the storms. The same gravity that tears at the rings. The same gravity that dominates everything within 100 million kilometers. Here, that violence becomes something else. A sustained heat source. An energy supply for an ocean that shouldn't exist. The plumes are still erupting. Right now, at this moment, water from an alien ocean is shooting into space. Some of it falls back as snow. Some of it escapes. Some of it drifts outward and becomes part of Saturn's rings. The moon is slowly losing its ocean to space, but tidal heating keeps melting more ice. The cycle continues. Cassini detected something else in those plumes, something that changed the conversation entirely. That changed everything. Because Enceladus wasn't just geologically interesting anymore, it became the most important moon in the solar system, and that created a problem. Cassini had been up there for 13 years. 13 years orbiting Saturn, sending back images, measuring magnetic fields, sampling ring particles, flying past moons. It launched in 1997, arrived in 2004. By 2017, it was running low on fuel. The spacecraft was old, not broken, not malfunctioning, just old, and running out of propellant. Without fuel, Cassini couldn't control its trajectory anymore. Eventually, it would drift, crash into something. Maybe one of the moons, maybe Enceladus. Scientists realized they had a decision to make. Let the spacecraft drift until it randomly collided with something, or end the mission deliberately. That sounds simple until you understand what was at stake. Cassini wasn't clean, not in the biological sense. It launched from Earth. It was built in clean rooms, sure, but no spacecraft is truly sterile. There are bacteria, microbes that can survive vacuum, organisms that can hibernate for decades in radiation and cold. Earth life is resilient in ways we're still discovering. If Cassini crashed into Enceladus, those microbes would contaminate the ocean. The same ocean that might harbor alien life. We'd be introducing Earth biology to the one place in the solar system where we have the best chance of finding something else, something that evolved completely separately. The mission would destroy the very thing it discovered. This is called forward contamination. We take it seriously, extremely seriously, because if we find life on Enceladus in 50 years, We need to know it's actually from Enceladus, not hitchhiking bacteria from a spacecraft we crashed there in 2017. Titan had the same problem. Liquid methane lakes, organic chemistry, less likely to harbor life than Enceladus, but possible. We couldn't risk it. Cassini spent 13 years orbiting Saturn, and then it died to protect the moons it had discovered. It was a suicide mission. Not because the spacecraft failed, but because it succeeded. We couldn't let it contaminate the very places where we might find life. The engineers designed something called the Grand Finale, 22 orbits between Saturn and its rings, diving through a gap that had never been explored, getting closer to Saturn than any spacecraft ever had, sampling the atmosphere, measuring the magnetic field at close range, collecting data that was impossible to get any other way. Then, on the final orbit, Cassini would plunge into Saturn's atmosphere and burn up, a complete destruction. Every microbe vaporized, no chance of contamination. The gap between Saturn and its rings is about 2,000 kilometers wide. That sounds generous, comfortable even. 2,000 kilometers is the distance from Los Angeles to Denver. You could fit 6 Earths side by side in that gap, but the rings are 282,000 kilometers across. Threading a gap 2,000 kilometers wide through a structure that massive while traveling at tens of thousands of kilometers per hour is absurd. It's like threading a needle while falling. And Cassini did it 22 times. Each dive took the spacecraft closer, skimming the cloud tops, flying through regions where ring particles might exist. Nobody knew if the gap was truly empty. One collision with a particle the size of a grain of sand at that speed would destroy the spacecraft instantly. 22 times, Cassini threaded that needle. 22 times, it survived, sent back data, climbed back out of Saturn's gravity well, prepared for the next dive. On September 15th, 2017, Cassini made its final plunge. This time, it didn't climb back out. It dove straight into Saturn's atmosphere. The spacecraft hit the upper atmosphere at tens of thousands of kilometers per hour, fast enough that the friction turned it into a fireball. The hull heated. The instruments failed one by one. Cassini kept transmitting, sending data until the signal cut out. Then it was gone. 20 years in space, 13 years orbiting Saturn, hundreds of thousands of images, and discoveries that rewrote textbooks, the detection of an ocean that might harbor life. All of it ended in seconds. Cassini didn't just run out of fuel and drift. It was vaporized. It ceased to exist as a spacecraft. The metal melted. The components broke apart. The atoms scattered into Saturn's atmosphere. Some of them are probably still falling, mixing with the clouds, drifting toward the core with the ring rain. $1 billion mission ended in a fireball to save the potential children of Enceladus. Most people don't know missions end this way. They think spacecraft just run out of power and go silent, drifting forever as space junk. That happens sometimes, but not when the stakes are this high. Cassini's destruction was deliberate, necessary, a final act of scientific integrity. We killed the mission because it worked, because it found something worth protecting. That's not failure, that's the opposite. I think about this sometimes when I look up. Cassini is still there, in a way. Its atoms are part of Saturn now, mixed into the clouds, falling toward the core with the ring rain. The spacecraft that showed us Saturn's secrets became part of Saturn. That feels right, somehow. The mission ended, but the discoveries didn't, because in those final dives, Cassini collected data from regions nobody had ever sampled, measurements from the gap between the planet and the rings, atmospheric composition at depths that were impossible to reach before. And in the years before the grand finale, during all those flybys of Enceladus, Cassini flew through the plumes, directly through the water erupting from the ocean. It sampled the chemistry. It analyzed what was in that water. What it found changed the conversation about life in the solar system completely. Cassini tasted Enceladus's ocean. It flew through the spray at 1,300 kilometers per hour and caught ice particles on its instruments. That's faster than a rifle bullet. The spacecraft was moving so fast that the ice grains hit like pellets, but they didn't damage anything. They just stuck, frozen to the sensors. And when scientists analyzed those particles, they found salt, organic molecules, and silica. That's the recipe for life, or at least the same ingredients as Earth's deep sea vents, where life thrives in total darkness. The spacecraft flew through the plumes 23 times. Each pass collected samples from different parts of the eruption, different heights, different angles, at different moments in Enceladus's orbit. Each time, the chemistry was consistent. Water ice made up most of the plume. That was expected, but mixed in with the ice were things nobody anticipated finding on a moon, barely 500 kilometers wide. Start with the salt, sodium chloride, table salt, the same stuff you sprinkle on food. It was everywhere in the plumes, not trace amounts, significant concentrations. That matters because salt doesn't just appear in water, it requires contact with rock. The water has to be sitting on a rocky surface, dissolving minerals, pulling ions out of stone. That takes time. It takes heat. It takes an ocean floor. Enceladus doesn't just have liquid water under the ice, it has a salty ocean in direct contact with a rocky core. The water is touching stone, dissolving it, becoming chemically active. And then there were the organics. Organic molecules are carbon-based compounds. They're not alive, but they're the building blocks of life, the stuff that eventually assembles into proteins, lipids, nucleic acids. Cassini found them in Enceladus's plumes. Not just simple organics either, complex molecules, chains with dozens of atoms, rings, structures. Someone opened the door to the ocean and threw a bucket of prebiotic chemistry into space, and we caught it. That's not a metaphor. The plumes are literally ejecting the raw materials of biology into the vacuum. We flew through it, sampled it, brought the data home. The organic molecules weren't a complete surprise. Comets have organics. Asteroids have organics. Titan's atmosphere is thick with them. Carbon chemistry happens all over the solar system, but context matters. Finding organics on a dry rock means nothing. Finding them in liquid water mixed with salts, erupting from an ocean in contact with a rocky seafloor, that's different. That's chemistry with potential. Then, Cassini found the silica, tiny particles of silicon dioxide suspended in the ice. That's the key. That's the thing that changed everything. Silica only forms under specific conditions. You need liquid water heated to at least 90 degrees Celsius. That's close to boiling. You need the water to be in contact with rock at high pressure. You need it to dissolve silica from the minerals, then cool down rapidly so the silica precipitates out as tiny grains. Those conditions exist in exactly one environment on Earth: hydrothermal vents, hot springs on the ocean floor, where superheated water erupts from cracks in the crust. Enceladus has underwater hot springs. On a moon 500 kilometers wide, orbiting a gas giant over 1 billion kilometers from the sun, there are hot springs on the seafloor. That's not supposed to be possible. Picture Earth's deep sea vents. Black smokers, they're called. Chimneys of mineral deposits on the ocean floor, belching water heated to 300 degrees Celsius. The water doesn't boil because the pressure is too high. It just pours out, superheated, carrying dissolved metals and minerals. When it hits the cold ocean water, everything precipitates. The minerals fall out of solution, build towers. Whole ecosystems live there. Tube worms 3 meters long, eyeless shrimp, bacteria that eat sulfur instead of light. Life that doesn't need the sun. Life powered by chemistry alone. That's what the silica particles suggest. Enceladus has the same system. Smaller, colder, but fundamentally similar. Water heated by contact with hot rock, chemical energy available, a habitable environment. Let me be clear about what that means. Habitable doesn't mean inhabited. It means the conditions are right. Liquid water, chemical energy, organic molecules. Those 3 things together create an environment where life could exist. Not life as some abstract possibility, life as we know it. The same biochemistry that works on Earth could work on Enceladus, right now, today, under the ice. Most people still think Mars is the best place to look for life. Mars gets all the attention, the rovers, the helicopters, the sample return missions. But Mars is a frozen desert. If there's life there, it's probably deep underground, sheltered from radiation, clinging to tiny pockets of moisture. Sampling it means drilling, digging, hoping you hit the right spot. Enceladus is different. Enceladus throws its ocean into space. The plumes rise 800 kilometers above the surface. You don't need to land. You don't need to drill. You just fly through and collect samples. Cassini proved that. It tasted the ocean without ever touching the moon. That makes Enceladus arguably the best place in the solar system to search for life, not because it's more likely to be inhabited than Mars or Europa or Titan. We don't know the odds, but because it's the easiest to sample. The ocean is right there, erupting, waiting. We could send a spacecraft designed specifically to analyze the plumes. Better instruments than Cassini had. Mass spectrometers that can identify amino acids. Our detectors sensitive enough to find biosignatures. We could do this with current technology. No landing required, no drilling. Just fly through and taste the water. The plumes contain everything needed for life as we know it. Liquid water, organic molecules, chemical energy from hydrothermal vents. That's the complete package. Enceladus is not just a moon with an ocean. It's a moon with a habitable ocean. Possibly right now, while you're reading this, while you're going about your day, there might be something living in the dark water under the ice. Something that doesn't know the sun exists. Something that has never seen a star. We don't know if anything actually lives there. The chemistry is right. The environment is right. But that doesn't guarantee life exists. It just means it could. Maybe the ocean is sterile, and maybe life never started. Maybe it started and died out. Maybe it's there now, thriving in the warmth near the vents, completely unaware that its home is a tiny moon, orbiting a giant planet, orbiting a distant star. We have no idea. That's the honest answer. We found the ingredients. We haven't found the cake, but finding a habitable environment beyond Earth, that alone changes the conversation. For centuries, we assumed life needed a planet like ours. Warm surface, thick atmosphere, stable climate. But Enceladus doesn't have any of that. It's a frozen moon. No atmosphere to speak of. Surface temperature around -200 degrees Celsius. And yet, beneath the ice, there's an ocean. There's heat. There's chemistry. There's possibility. The requirements for life are more flexible than we thought. Habitability isn't about being Earth-like. It's about having the right chemistry in the right conditions. And those conditions might be common in the outer solar system, hidden under ice, warmed by tidal forces, protected from radiation, waiting. For centuries, we thought we had it figured out. Life needs liquid water. Liquid water needs a certain temperature range, and that range only exists at a specific distance from a star. Too close, everything boils. Too far, everything freezes. There's a zone in the middle where conditions are just right. We called it the habitable zone, the Goldilocks zone. Not too hot, not too cold. For our sun, that zone sits roughly where Earth orbits, about 150 million kilometers out. Venus is too close. Mars is borderline. Earth is perfect. That was the model. And that was the assumption we carried into the search for life beyond our solar system. Find a planet in the habitable zone of its star, and maybe you find life. Then we looked at Enceladus. Enceladus orbits Saturn at a distance of about 238,000 kilometers from the planet. But Saturn itself is nearly 1.5 billion kilometers from the Sun. That's almost 10 times farther than Earth. At that distance, sunlight is weak. Temperatures are brutal. The surface of Enceladus sits around -200 degrees Celsius. By every traditional metric, it should be a dead, frozen rock. No liquid water, no chemistry, no chance. But beneath the ice, there's an ocean, a real ocean. Liquid water, warm vents, organic molecules, chemistry happening in the dark. Tidal heating broke the rules. The gravitational squeeze from Saturn keeps that ocean liquid. Not the sun, not starlight, just gravity. Just the constant flex and pull of tidal forces generated by Saturn's massive presence. The heat comes from the moon's own interior, friction caused by the planet it orbits. Distance from the sun doesn't matter. The traditional habitable zone doesn't apply. We used to think the habitable zone was a belt around a star, a narrow ring where temperatures allowed liquid water on a surface. But Enceladus is nearly 1.5 billion kilometers from the sun, and it has a liquid ocean. Tidal heating rewrote the requirements. Habitability isn't about distance from a star anymore. It's about having the right kind of moon orbiting the right kind of planet. It's about gravitational relationships. It's about being squeezed. This changes everything. Europa, one of Jupiter's moons, has the same setup. It orbits Jupiter far beyond the Sun's habitable zone. Surface temperature, -160 degrees Celsius. Frozen solid on top. But underneath, there's an ocean, probably deeper than any ocean on Earth, kept liquid by the same mechanism. Tidal heating, gravitational flex. Jupiter squeezes Europa the way Saturn squeezes Enceladus. 2 moons, 2 different gas giants. Same principle. Both have liquid water oceans in places where liquid water shouldn't exist. Imagine if Earth had no sun, but we orbited Jupiter so closely that tidal forces kept our oceans liquid. We'd still have life, it just wouldn't depend on sunlight. Plants wouldn't exist. Photosynthesis wouldn't be the base of the food chain. And as but near hydrothermal vents on the ocean floor, life would thrive. Bacteria feeding on chemical energy, larger organisms feeding on the bacteria. A whole ecosystem in the dark, powered by gravity, not photosynthesis. That's the Enceladus model. Life in the dark, life without a star. We spent centuries assuming life needed a sun. Turns out life just needs heat, water, and chemistry. The sun is optional. That's either humbling or embarrassing, depending on how you look at it. Probably both. The implications stretch far beyond our solar system. Every gas giant with large moons is potentially a habitable system. Not the planet itself, the moons. The smaller bodies caught in gravitational dances with their massive hosts. We've been looking at solar systems wrong. The habitable zone isn't a ring around a star, yet it's anywhere a moon can be squeezed by tidal forces. Anywhere gravity can generate heat. That expands the possibilities dramatically. In our galaxy alone, there are hundreds of billions of stars. Many of those stars have planets. Many of those planets are gas giants. And many of those gas giants have moons. If even a fraction of those moons experience tidal heating strong enough to maintain subsurface oceans, the number of potentially habitable worlds jumps by orders of magnitude. We thought habitable meant Earth-like, a rocky planet with a thick atmosphere orbiting a star at just the right distance. But that's only one model, one path to habitability. Moons like Enceladus represent another path entirely, hidden oceans. No atmosphere required, no surface habitability needed, just water, heat, and chemistry beneath an icy shell. Yet the traditional Goldilocks zone isn't obsolete, it's just incomplete. Surface habitability still matters for planets like Earth, but subsurface habitability matters for moons. And there might be far more moons than Earth-like planets. We only realized this because Cassini flew through the plumes of Enceladus and detected organic molecules. Before that, we weren't looking for life in the outer solar system. We assumed it was too cold, too far from the sun, too hostile. We were wrong. The search for life has expanded. It's not just about finding planets in the habitable zone anymore. It's about finding moons around gas giants. It's about detecting the signatures of subsurface oceans. It's about looking for plumes, geysers, anything that hints at liquid water beneath an icy crust. Enceladus taught us where to look. Europa confirmed the lesson. Now we're searching for the same signs around gas giants in other solar systems. Every gas giant with large moons is now a target, not because the planet itself might be habitable, but because its moons might be. The gas giant acts as a gravitational anchor, a source of tidal heating, a miniature system within the larger solar system. And within that miniature system, habitability doesn't depend on the star. It depends on the relationship between planet and moon. That's a fundamentally different way of thinking about where life can exist. Distance from a star used to be the primary factor. Now it's one factor among many. Tidal heating, subsurface oceans, ice shell thickness, geological activity. All of these matter. All of these contribute to habitability in ways we didn't appreciate before. As Saturn's moons showed us this, they forced us to expand our definition of what a habitable world looks like. Not a blue marble bathed in sunlight, maybe an ice-covered moon in the outer reaches of a solar system, warmed from within by the gravitational pull of a giant planet. Hidden, dark, but alive. We don't know if life actually exists on Enceladus or Europa. We haven't confirmed it, but we've confirmed the environments could support it. And that's enough to change how we search, how we think, how we define the boundaries of life's possibilities. The universe just got a lot more interesting, and a lot more crowded with potential. We've spent most of this documentary talking about what Saturn is, what it does, what happens in its storms and on its moons. But here's something worth stopping for. How do we actually know any of this? How do humans, sitting on a rock 93 million miles from the sun, figure out what's happening on a planet 1.2 billion kilometers away? The answer is more complicated than you might think, and more fragile. When you look at Saturn through a telescope, you see rings, but you don't see the 10-meter thickness. You don't see trillions of individual ice chunks. You see a disk, solid and smooth, because your eyes lie to you. The truth requires a spacecraft, or at least math. Even with a good amateur telescope, the kind someone might set up in their backyard, Saturn looks peaceful, serene. The rings appear as a flat band, sometimes tilted, sometimes edge on. If you're lucky and the seeing conditions are good, you might spot Titan, a tiny dot of light near the planet. That's it. And that's what direct observation gives you. The hexagon at Saturn's north pole, invisible from Earth, the great white spot that erupts every few decades, only visible during the rare years it happens, and even then, just as a pale smudge. The bands in Saturn's atmosphere, you can see them, but not the details, not the wind speeds, not the lightning, not the vertical structure. From Earth, Saturn is beautiful, but it's also mostly a mystery. Everything else we know comes from spacecraft, the Voyager flybys in the 1980s, the Cassini mission from 2004 to 2017. 13 years of data. That's what Cassini gave us. 13 years out of 4.5 billion years. Saturn has been orbiting the Sun since the solar system formed. We observed it for 13 years. Do the math. We saw 1/13 billionth of its life. Imagine if aliens observed Earth for 13 years and tried to understand all of human history from that sample. All of civilization, all of evolution, all of climate change and ice ages and mass extinctions. From 13 years, we're doing the same thing to Saturn. And even during those 13 years, Cassini couldn't see everything. It orbited Saturn, yes, but the planet is enormous. So the ring system spans 282,000 kilometers. The magnetosphere is even larger. Cassini was one probe, one set of instruments. It could only be in one place at a time. Most of what we know about Saturn isn't from direct photographs. It's from inference, from measurements, from detective work. Take Enceladus. We've never seen the hydrothermal vents on its seafloor. We've never sent a camera down into that ocean. We know the vents probably exist because Cassini flew through the plumes shooting out of the South Pole. It analyzed the chemistry, water vapor, salt, organic molecules, silica particles. That chemistry tells a story. It says there's liquid water in contact with a rocky core. It says there's heat. It says there are chemical reactions happening that, on Earth, support life. But we haven't seen it. Yet we're detectives investigating a crime scene 1.2 billion kilometers away, and we can't visit. We just collect clues and build a case. The same goes for Titan. We've never seen a methane wave crash on Titan's shore. We've never watched rain fall from those orange skies. Cassini's radar mapped the surface. It saw the lakes. It measured their depth using radio waves. The Huygens probe landed in 2005 and sent back pictures for 90 minutes before its battery died. 90 minutes. On a moon with weather and rivers and maybe even volcanic activity. We saw one spot, one moment, and from that, we extrapolate. We build models. We make educated guesses about what the rest of Titan looks like. Even Saturn's interior is invisible. We can't drill down into a gas giant. We can't send a probe into the core. Everything we think we know about what's inside Saturn comes from gravity measurements and math. Cassini tracked how Saturn's gravity tugged on the spacecraft. Scientists used those tiny variations to infer the planet's internal structure, how much mass is in the core, how dense the metallic hydrogen layer is, how the different layers rotate at different speeds. It's brilliant work, but it's not direct observation. It's inference based on equations and assumptions and models that might be wrong. Here's the part that doesn't get talked about enough. Most of what we know about Saturn isn't actually known. It's inferred. It's our best explanation given the data we have. The public sees Cassini images and assumes we have comprehensive knowledge, that we've figured Saturn out. But the truth is, we've sampled a tiny fraction of its existence. We've measured what we could measure with the instruments we had, and we've filled in the gaps with models. Some of those models are probably right, some are probably close, and some, we'll find out later, were completely wrong. Spectroscopy tells us what chemicals are in Saturn's atmosphere, but it doesn't tell us how those chemicals move, how they interact at different depths, how they change over time. Radio emissions tell us Saturn has a magnetic field, but we don't fully understand why it's almost perfectly aligned with the planet's rotation axis. That's weird. It shouldn't be that way. We have theories, but theories aren't certainties. The rings are the same. We know they're made of ice. We know they're thin. We know there are gaps and waves and shepherd moons. But we don't know exactly how old they are. We don't know if they'll last another 100 million years or disappear in 10 million. We have estimates, ranges, best guesses, not answers. And there are things we may never observe directly. The core of Saturn, if it exists as a distinct object, is buried under tens of thousands of kilometers of gas and liquid. We'll never see it. Not with current technology. Maybe not ever. The bottom of Enceladus's ocean is hidden under kilometers of ice. The surface of Titan is hidden under that thick atmosphere. Even with Cassini, even with all our instruments, we're still looking at Saturn from the outside, peering in, guessing. This isn't a failure of science. It's the reality of studying distant worlds. We do the best we can with the tools we have. We take measurements, we build models, and we test predictions. And slowly, piece by piece, we construct an understanding. But that understanding is always incomplete, always provisional, always subject to revision when new data comes in. When you watch footage from Cassini, remember what you're seeing: a snapshot, a moment, one perspective out of billions of possible perspectives, one spacecraft's view of a planet that's been churning and evolving for longer than anything on Earth has existed. We're not observing Saturn comprehensively. We're sampling it, taking a few sips from an ocean and trying to describe what the ocean tastes like. That's humbling, but it's also part of what makes this work meaningful. We're reaching across the solar system with radio waves and cameras and spectrometers, trying to understand a place we'll probably never visit. Yet we're building knowledge from fragments, from clues, from light that traveled for over an hour just to reach our instruments. And somehow, it works. Not perfectly, not completely, but enough to see the outlines of something vast and strange and still mostly unknown. That understanding is incomplete. It always will be. There are questions we can't answer yet, questions we might never answer. And that's not a failure. That's just where we are. Start with the hexagon, that six-sided storm at Saturn's North Pole. We've watched it for decades. Voyager saw it in 1980. Cassini watched it from 2004 to 2017. It never drifted, never lost its shape, never became a pentagon or an octagon, just a perfect hexagon, sitting there, spinning. And we don't know why. We have models, theories, simulations that can produce hexagonal patterns in rotating fluids, standing waves in jet streams, interacting at specific speeds and pressures. The math works, the physics checks out, but we don't have certainty. The hexagon is the greatest meteorological mystery in the solar system. We can explain why jet streams exist. We can explain standing waves in fluids, but a perfect hexagon that never drifts, never dissipates. For decades, we have models, but no certainty. It's like finding a snowflake the size of a continent that never melts. Something about the conditions at Saturn's pole locks that shape in place. Something about the rotation speed, the temperature gradient, the atmospheric composition. But which factor matters most? Which ones are essential and which are incidental? We're still figuring that out. But think about what that means. We can send a spacecraft to Saturn. We can orbit for 13 years. We can photograph the hexagon from every angle, in every wavelength, and we still can't explain it with complete confidence. That's humbling. Then there's Enceladus, that tiny moon with the subsurface ocean. the one spraying water geysers into space. We know there's liquid water down there. We know there are hydrothermal vents. We know there are organic molecules. Everything you need for life, but we don't know if life is actually there. If there's life in Enceladus's ocean, it would be the second Genesis. Life that arose independently from Earth. That would mean life is common in the universe, not a fluke. But we can't drill through 20 kilometers of ice to check. We have to wait for a future mission. Or hope Enceladus keeps spraying its ocean into space and we can catch something alive. Cassini flew through those geysers multiple times. It analyzed the water, the chemistry, the organic compounds. But it wasn't designed to detect life. Its instruments couldn't tell the difference between a dead amino acid and a living cell. We got tantalizingly close to answering one of humanity's biggest questions, and we couldn't quite reach it. The next mission might. The proposed Enceladus Orbolander would orbit the moon, fly through the geysers repeatedly, and eventually land near one of the fissures where water erupts. It could sample fresh ocean water. It could look for biosignatures, for metabolism, for cells. But that mission hasn't been funded yet. It might launch in the 2030s. Maybe the 2040s, maybe never, as we're talking about decades. At minimum, an entire generation might grow up and grow old before we know if there's life in Enceladus's ocean. That's the reality of deep space exploration. You don't get answers quickly. Then there's the rings themselves. We know they're young. We know something was destroyed to create them. A moon that wandered too close, or a captured comet that got shredded. But we don't know which one. We can't identify the victim. We'll probably never know which specific moon became the rings. It happened millions of years ago, and the evidence was shredded into trillions of pieces. It's a cold case with no witnesses and a crime scene that's been trampled for eons. We can say it happened. We can't say who the victim was. The rings are made of water ice. That tells us something. And most of Saturn's moons are water ice. Most comets are water ice. The chemistry doesn't narrow it down. The size estimates don't help much either. A small moon or a large comet would both produce enough material. We're left guessing. There are other mysteries, smaller ones, but still unsolved. How deep is Titan's subsurface ocean? We know there's liquid water beneath the surface, under the crust, below the methane lakes, but we don't know how deep it goes. 10 kilometers? 100? Is it a thin layer or a global ocean thicker than Earth's? We have gravity measurements, seismic estimates, but no direct observations. What causes the spokes in the B-ring, those radial patterns that appear and disappear over hours? We think it's electrostatic forces lifting dust above the ring plane. We think it's related to Saturn's magnetic field, but we're not certain. The spokes showed up in Voyager images, disappeared for years, came back during Cassini's mission. Why do they come and go? We don't really know. That's the honest answer. Why does Saturn radiate more heat than it receives from the Sun? We think it's leftover heat from formation, still leaking out. We think helium rain inside the planet releases gravitational energy as it falls, but the numbers don't quite match. There's more heat than our models predict. Something else is happening inside Saturn, something we haven't accounted for. These aren't trivial questions. They're fundamental. They're about how planets form, how atmospheres behave, how life begins. And we can't answer them yet. Maybe we will. Maybe new missions will bring new data. Dragonfly, the proposed Titan drone, it could launch in the 2020s and arrive in the 2030s. It would fly across Titan's surface, sampling the chemistry, looking for prebiotic molecules. That might tell us something about the subsurface ocean. It might not. The truth is, nobody's certain. We're in a waiting period. Cassini ended in 2017. The next Saturn mission won't arrive for decades. We're living on old data, analyzing and reanalyzing images from a spacecraft that burned up 7 years ago, looking for patterns we missed the first time, finding new questions in old answers. Some of Saturn's biggest mysteries may never be answered with current technology. The hexagon's exact mechanism, the identity of the destroyed moon, and the presence of life in Enceladus are questions that may require decades or centuries to resolve, if they can be resolved at all. Science has limits, and patience is required. That's not a comforting thought. We want answers. We want to know. But the universe doesn't care what we find convenient. Saturn keeps its secrets. It spins and storms and radiates heat, indifferent to our curiosity. What we're left with is uncertainty, provisional knowledge, the best answers we can construct from incomplete data. That's not failure. That's just the nature of exploration. You go as far as you can with the tools you have. You learn what you can learn, and you accept that some questions will outlive you. Saturn isn't finished revealing itself. There's more to find, more to understand, but it will take time and effort and missions that haven't been built yet. Until then, we sit with what we know and what we don't. We've spent all this time looking at Saturn itself, the storms, the rings, the moons. But step back for a moment. Look at the bigger picture. Saturn doesn't exist in isolation. It's part of a system, a family of planets that grew up together, moved around, shaped each other's fates. And Saturn's role in that family has been enormous, more enormous than most people realize. Saturn is the second largest planet in the solar system. Only Jupiter is bigger. Together, they dwarf everything else. Saturn has 95 times the mass of Earth. Jupiter has 318 times. When you add up all the planets, moons, asteroids, and comets in the solar system, Jupiter and Saturn account for more than 92% of the total mass. Everything else is rounding error. They're not just big planets. They're the only planets that really matter, gravitationally speaking. The inner rocky worlds, the ice giants beyond, they're all living in the shadow of Jupiter and Saturn's influence. Saturn formed early, within the first few million years of the solar system's existence. Gas giants have to form fast before the disk of gas and dust disperses. Miss your window and you don't get to be a gas giant. Saturn didn't miss. It grew quickly, pulling in hydrogen and helium, building up mass. And once it had that mass, it started moving things around. Planets don't stay where they form. They migrate. Saturn moved inward, then outward, dragging other planets with it through gravitational interactions. Uranus and Neptune might have swapped places because of Saturn and Jupiter. The asteroid belt might exist because Saturn's gravity prevented those rocks from ever forming a planet. We're still piecing together the details, but one thing is clear. Saturn reshaped the solar system. Here's something most people don't think about. Saturn spins so fast that it's noticeably squashed. One day on Saturn is 10.5 hours, less than half an Earth day. If you could see Saturn from the side, you'd notice it's fatter at the equator than pole to pole. It's spinning itself into an oval. The equator bulges outward because of the centrifugal force. Saturn is visibly oblate. You can see it in photographs. It's not a sphere. It's a flattened ball, stretched by its own rotation. That low density we talked about earlier, the fact that Saturn would float in water, that contributes too. There's not enough internal rigidity to resist the spin. Saturn is loose, soft, and it shows. That rapid rotation and low density make Saturn the most oblate planet in the solar system. The equatorial diameter is about 10% larger than the pole-to-pole diameter. 10%. That's not subtle. If Earth were that oblate, the difference would be noticeable from space. But Earth is dense and spins slowly, so it stays mostly round. Saturn doesn't have that luxury. It's a giant spinning fast, and physics doesn't care about appearances. Saturn and Jupiter are the solar system's bouncers. Their gravity flings comets and asteroids around, sometimes into the sun, sometimes out of the solar system entirely. Without them, Earth would be hit far more often by extinction-level impacts. We owe our survival, in part, to Saturn's gravity clearing the neighborhood. This isn't speculation. Models show it clearly. Remove Jupiter and Saturn, and the inner solar system becomes a shooting gallery. Comets from the outer regions would rain down on Earth, Venus, Mars. The impact rate would be orders of magnitude higher. Life might never have had the stable environment it needed to evolve, or it might have been wiped out repeatedly before anything complex could develop. What would Earth's history look like if Saturn didn't exist? More impacts, more mass extinctions, maybe no humans. We don't think about it, because Saturn just is. But its existence is one of the reasons we're here to think about it at all. That's worth sitting with for a moment. Saturn isn't just protecting us now. It's been doing this for 4.5 billion years, since the beginning. Every comet it ejected, Every asteroid it nudged into a different orbit, every gravitational assist that sent something harmless into the outer darkness, that's one less threat to Earth. We're not looking at a peaceful planet. We're looking at a guardian. A violent, indifferent guardian that doesn't know we exist and wouldn't care if it did, but a guardian nonetheless. This protection isn't perfect. Things still get through. The dinosaurs can attest to that, but it's better than nothing. Much better. And it's not just Earth. Mars benefits too. Venus, Mercury, the whole inner solar system lives in a safer place because Saturn and Jupiter exist. When we discover gas giants around other stars, we use Saturn and Jupiter as reference points. But most exoplanet gas giants are far stranger, orbiting closer to their stars, hotter, more massive, hot Jupiters, they're called. Gas giants that orbit their stars in days, not years, temperatures in the thousands of degrees, atmospheres stripped away by stellar wind. Saturn is weird, but it's our weird. It's the prototype we compare everything else to, and by comparison, Saturn is almost normal, almost tame. It's in a stable orbit, far from the Sun, with intact rings and dozens of moons. Many exoplanet systems have gas giants that migrated inward, disrupting everything in their path. Rocky planets swallowed, asteroid belts scattered, entire systems thrown into chaos. Saturn stayed put. More or less. That's luck, cosmic luck. We got a solar system where the gas giants settled into distant, stable orbits, leaving room for rocky planets to survive. Not every system gets that. As studying Saturn teaches us what gas giants can be, how they form, how they evolve, how they affect their surroundings. Every mission to Saturn, every image, every measurement adds to our understanding of planetary systems in general. When we look at exoplanets, we're not just guessing. We have Saturn, we have Jupiter, we have data, real data from real gas giants. And that data tells us that planets are more dynamic, more violent, more unpredictable than we thought. Saturn looks stable now, but its history is chaotic. Migration, collisions, moons destroyed, rings formed. Stability is temporary, a moment in deep time. Saturn is peaceful the way a sleeping volcano is peaceful. Quiet now, but not inert. There's a perspective shift that happens when you think about Saturn this way. It's not just a distant object, and not just something to look at through a telescope. It's part of the machinery that made Earth habitable, part of the reason we're here. And it's a window into how other planetary systems work, how gas giants shape the worlds around them, how rare or common our setup might be. Saturn's gravity, its mass, its position, they all matter. They've always mattered, and they'll keep mattering long after we're gone. Saturn will still be there, spinning too fast, protecting the inner planets, keeping the solar system's balance. Silent, indifferent, essential. We started with a simple idea. Saturn looks peaceful. It looks serene, golden and calm and perfect through a telescope. But we know the truth now. Saturn is a beautiful lie. The beauty is real. That's the thing. It's not a trick. The rings genuinely are stunning. The hexagon storm genuinely is one of the most bizarre structures in the solar system. The moons genuinely hold the possibility of life. All of that is true, but the violence is just as real. The chaos. The lightning 10,000 times more powerful than ours. The moons being torn apart by gravity. The diamond rain falling through hydrogen skies. The rings dying, particle by particle, falling as rain into the planet below. Both things exist at the same time. Beauty and destruction. Peace and violence. We just couldn't see the second half until we got close enough. Cassini changed everything. Before that mission, Saturn was a postcard, something beautiful to look at and move on from. Cassini spent 13 years there. It watched storms erupt. It flew through geysers shooting from an ice moon. It measured the rain falling from the rings. It found an ocean under ice and lakes of methane, and a planet spinning so fast it's flattened itself. And then, when it ran out of fuel, it dove into Saturn's atmosphere and became part of the system it studied. Cassini is part of Saturn now. Ash, vapor, atoms mixed into the hydrogen and helium. ESA, the spacecraft that revealed Saturn's violence, became another piece of debris in a system built on destruction. The rings won't last forever. We know that now. They're young, a few 100 million years old at most. They didn't exist when dinosaurs walked Earth, and they won't exist in another few 100 million years. They're temporary, a brief flicker in Saturn's 4.5 billion year history. We are living in a privileged moment of cosmic history. A few million years earlier, and Saturn would have been ringless, a gas giant like any other. A few million years later, and the crown jewel of the solar system will be gone. We won the lottery. We just didn't know we'd bought a ticket. Think about that. Every image of Saturn, every photograph, every painting, every time someone has looked through a telescope and felt that sense of wonder, all of it is happening during this narrow window. The rings exist now, right now, for us, and they're already dying. The rain has been falling for millions of years. It will keep falling, slowly, invisibly, until one day there's nothing left, just a memory in geology, evidence in the chemistry of Saturn's upper atmosphere, a ghost. The search continues, on Enceladus, on Titan, in the data Cassini sent back before it fell. We're looking for life, for chemistry that might hint at biology, for anything that suggests we're not alone. We might find it, we might not, but the search itself matters. Every measurement, every analysis, every comparison to Earth, it all adds up. Saturn teaches us what's possible, what planets can become, what moons can hide, and what temporary beauty looks like on a cosmic scale. Saturn is a masterpiece of destruction that happens to be beautiful. That's the only way to say it. The rings are the shattered remains of something that used to exist. The storms are chaos made visible. The moons are laboratories of extremes. And we get to witness it right now, in this brief moment when the rings still exist and we're advanced enough to study them, but not so far in the future that they're gone. Everything about this system is temporary. The rings are falling. The moons are migrating. Saturn itself is slowly cooling, slowly changing, spinning through space in a solar system that won't last forever, but for a brief window. This window, right now, it's the most beautiful thing in the solar system, and we got to see it. That has to mean something. If you enjoyed this exploration of Saturn's hidden violence and temporary beauty, consider subscribing for more deep dives into the universe's most fascinating objects. Thank you for listening. Somewhere above Saturn, right now, particles of ice are falling, slowly, silently, raining down into the planet, the rings dying one piece at a time.